Welcome to a deep dive into state space modeling. You've given me quite a stack of sources on this, so it seems like we're really going beyond just the basic definitions. We're going to explore how this framework helps us understand and even control dynamic systems. Like think robots, self-driving cars, heck, even a simple pendulum.
Yeah, it's really fascinating how state space modeling can break down these complex systems into pieces that we can actually work with. It's more than just equations. It's about seeing that underlying story, like how a system holds and releases energy, reacts to inputs, and how we can actually influence its behavior.
I've noticed that all these sources really emphasize this idea of state, but what does that actually mean in this context?
Imagine you're taking a snapshot of a system at just one moment. That snapshot, that's its state. It basically holds all the vital information you need to predict how it'll change over time. Think of like a car, its position on the road, its speed, how fast it's speeding up or slowing down, the acceleration. Those three variables together, that's the car's state.
So if you know those three things, you could predict where the car would be in the future, even if, say, the driver hits the gas or the brakes.
You got it. It's like having a crystal ball, sort of. Knowing the state lets you forecast what'll happen next. And this isn't limited to cars. Take a pendulum, for instance. Its state, that's determined by its angle, how far it is from hanging straight down, and its angular velocity, how fast it's swinging.
Oh, okay, so those would be what are called the state variables for those systems.
Exactly. State variables are like the chosen few, the specific quantities that perfectly describe the system's conditions at any given time. The key is they got to be independent, no redundancy. For a complete picture, you can't have any overlap in the information they provide.
Now, and I've seen some sources mention this connection between energy and the number of these state variables a system needs. Can you shed some light on that?
That's a fundamental idea. Every dynamic system, it stores energy somehow. Think about like a stretched rubber band, that's potential energy it's holding, or a spinning flywheel, that's kinetic energy. To completely describe a system, you need a state variable for every way it stores energy.
So if a system has two ways of storing energy, we need two state variables.
Generally, yes, though it can get a bit trickier when those energy storage mechanisms are like linked together. Think of a car suspension. You have springs and shock absorbers all working as one.
Okay. So to start building a state space model, we got to first identify every energy storing component in the system, kind of like taking inventory of its energy bank accounts, right?
That's a fantastic way to put it. Each one of those energy storing elements, it contributes to the overall state of the system. And once we've identified them all, well, then we can start describing how they behave mathematically.
So for a simple spring, like we'd use Hooke's law, right? That equation that connects the force the spring exerts to how much it's stretched or compressed.
Right. That equation, that becomes a building block in our state space model. And if we're talking about a mass, we'd bring in Newton's second law. That tells us how its acceleration is related to all the forces acting on it.
It sounds like what we're doing is breaking down this complicated system into these simpler parts, each with its own equation. But then what? What's the next step?
Well, the magic really starts when you connect all those equations. You got to consider how they influence each other and how they respond to things coming from outside the system. Those external inputs, like imagine our car example, pressing the gas pedal, that's an input. We need to link that action to how it affects the car's speed, its acceleration, which are those state variables we talked about.
So we're making like a network of relationships between these equations, showing how they all kind of push and pull on each other over time.
Exactly. That network, that's the heart of our state space model. It captures how the system acts, how it changes and evolves based on inputs and its own internal state.
This is starting to click. It's like we're drawing up a blueprint of the system, right? Showing all the connections and how everything responds to forces outside of it.
A blueprint. Yeah, that's a great analogy. The state space model, it really is a powerful tool. You can use it to predict how the system will behave. And it's great because you can then simulate different scenarios, test different control strategies, optimize things, and all of this without having to build expensive prototypes or do risky tests in the real world.
Now, these sources highlight two really key concepts, controllability and observability. What exactly do those mean when we're talking about state space models?
Yes, those are crucial. Controllability, that basically asks, can we steer our system to any state we want using just the inputs we have? Think back to the car. If you can move it anywhere you want on the road using the steering wheel and pedals, then boom, that car's controllable.
So a remote-controlled drone that can fly anywhere within its range, that'd be considered highly controllable. While like a train stuck on a track, that'd have pretty limited controllability.
Perfect examples. Now, observability, that asks a different question. Can we figure out the system's state just from the measurements we can take? Imagine you're driving that car again. If you can figure out your speed and location just by looking at the speedometer and the GPS, then your car is observable.
So if we had sensors on a robotic arm telling us the angle of each joint, we could use that to determine the arm's overall position, right? Which would make it observable.
You nailed it. But there's a catch. Measuring every single state variable can be pretty impractical or just plain expensive.
So there are trade-offs to think about.
Always. Out in the real world, we often have to just measure some key states, the really important ones. Then we estimate the rest based on those measurements and the model itself.
I bet that estimation process can be pretty tricky. What are some of the challenges there?
The big one is accuracy. Errors in our measurements or even errors in the model itself, those can lead to estimates that aren't so reliable. And the more complex the system, the harder and more computationally expensive it becomes to get those estimates.
So even with this powerful tool, we still need good engineering judgment and really understand the system we're trying to work with.
Absolutely. Choosing the right state variables in the first place, accurately modeling the system, picking the right techniques for estimation, these are all key for creating a state-space model you can trust.
Now, looking at these sources, there are quite a few methods for actually creating these models. Some look a lot more complex than others.
Oh, that's for sure. There's no one-size-fits-all here. The best method really depends on the system itself, what data we have, and how accurate we need to be.
Can you give us a rundown of, the most common approaches?
Sure. Let's start with what a lot of people consider the gold standard, deriving the model straight from first principles. Sometimes it's called the physics-based approach.
So with this first principles method, it sounds like we're getting down into the nitty-gritty physics of the system.
Exactly. It means you really need to understand those fundamental laws that are governing how it behaves, like Newton's laws of motion for something mechanical, or Kirchhoff's laws for electrical circuits, or even just basic conservation of energy principles.
I can see how that would give you, an accurate model, one with a lot of insights, but it probably takes quite a bit of expertise, right?
You got it. The great thing about the first principles method is that you get this really deep understanding of what makes the system tick, because you're modeling those underlying mechanisms directly. And that can be incredibly useful for designing things, for analyzing things.
But I imagine it can be a real-time sync, huh? Especially for those really complex systems where you have a ton of components interacting.
That's true. Building the model from scratch, it's label intensive. And you need a strong background in physics or engineering. And you know what? Even small mistakes in your equations, those can snowball into big errors in the model.
Okay, so what are the alternatives then? What if we don't have the time or the expertise to do a full-on first principles approach?
Well, one common alternative is to convert an existing transfer function.
Transfer functions. Those are those classic black box representations, right? You know what you put in and you know what comes out, but you have no idea what's happening inside.
Precisely. A transfer function, it describes that input-output relationship, but it doesn't tell you anything about the internal workings or even what the state variables are.
So how do we go from this black box to a state space model that actually gives us a peek inside?
There are a bunch of well-defined mathematical techniques that let us convert a transfer function into that state space representation. And it's generally pretty straightforward, especially if you're working with linear time-invariant systems.
That sounds convenient, but you did say linear time-invariant. What if our system isn't so well behaved?
That's the big limitation of starting with transfer functions. If you have a system with nonlinearities in it, like think about friction or saturation or hysteresis, those kinds of things, well, this method just won't cut it. And another thing is that the state variables in the converted model, they might not have any direct physical meaning, so it could be harder to really grab what's going on.
Gotcha. So what if we're dealing with something really complex, something that's tough to model analytically? Maybe it's super nonlinear, or maybe we just don't fully understand the physics behind it. What do we do then?
In those cases, system identification could be your best friend. It's all about using data to build your state space model.
So instead of starting with equations and all those physical laws, we let the data guide us.
Exactly. You feed experimental data into special algorithms, and those algorithms try to estimate the state space model that fits that data best. It's like the computer is learning about the system directly from the data itself.
That seems really powerful for real-world systems, the ones that are kind of messy and don't always play by the rules. But I'm guessing there are some downsides.
The main challenge with system identification is that you're really dependent on having good data, a lot of it. And it needs to be accurate and cover the full range of how the system operates. If your data is noisy or if it's incomplete, you could end up with a model that's, well, pretty lousy.
And I'm guessing this whole process can be a bit of a computational beast, right? Especially for complex systems where you're dealing with mountains of data.
True. System identification algorithms, they can be computationally intensive. And picking the right algorithm for your specific system and your data set, that's a key decision.
Okay, so we've talked about three methods now. First principles, converting a transfer function, and system identification. You mentioned a couple of others, right?
Right. The fourth approach involves using software. Think of like MATLAB, Simulink. These tools, They give you a lot of power for building and analyzing state space models.
So here it's all about leveraging the power of computers to make things easier for us.
You got it. They can automate a lot of that modeling process, and that saves time and, reduces the chances of making those pesky human errors. They also have some really cool visualization tools that help you understand and debug the model.
But I bet there's a learning curve with these programs,
Oh,
right?
there definitely is. You have to invest some time to learn the ins and outs of the software, but you always have to remember these are just tools. You still got to understand those state-space modeling principles to use them effectively.
Makes sense. Okay, so what about that last approach? What's the fifth tool in our modeling toolkit?
That's the hybrid method, and this one's probably the most flexible. It's all about combining different techniques, playing to the strengths of each one.
So, for example, we could use first principles for parts of the system that we really understand well, and then switch over to, say, system identification for the parts that are more complicated or where we have tons of data.
Exactly. Hybrid approaches let you be adaptable. You can tailor the method to the quirks of your system. Use the best and most efficient technique for each piece of the puzzle.
It sounds super powerful, but I bet it's also pretty tough to manage.
It can be, but the flexibility you get often outweighs the challenges. Of course, when you're integrating models from different methods, you got to be really careful. You need to plan it out, validate everything to make sure it's consistent, and avoid introducing errors.
So it's like putting together a jigsaw puzzle, right? Carefully choosing the right pieces, fitting them together perfectly, and making sure you end up with a complete picture of the system.
I like that, a jigsaw puzzle. And just like with any big project, there are some common traps you got to watch out for when you're building these models, no matter what method you choose.
Like what? What are some things that can trip us up?
Well, one mistake people often make is choosing the wrong state variables. Remember, the ones you pick have to fully capture how the system stores energy and how it behaves dynamically. Miss a key variable. Well, your model's not going to accurately represent how the system works.
So it's not just about spotting those energy storing components, but also picking the right variables to describe what's happening with them. What else should we be careful about?
Another common pitfall is going overboard, making the model way too complicated. It's tempting to include every little detail, but that can make it really hard to analyze and really computationally expensive.
So it's all about striking a balance between getting the right level of accuracy and keeping things simple.
Exactly. We want a model that captures the essence of how the system behaves, but we don't want to get bogged down in details that don't really matter.
Now, what about nonlinear systems? Can state space models handle those?
A lot of real-world systems, they're nonlinear, and if you try to force a linear model onto a nonlinear system, you're going to get predictions that are just plain wrong. We need to recognize those limitations and think about using nonlinear state space modeling techniques when we need to.
Gotcha. Any other challenges we should keep in mind?
Yeah, sometimes you run into numerical issues, especially when you're dealing with systems that have a lot of variables or, systems with stiff dynamics. That means some parts of the system change a lot faster than others. These issues, they can show up as instabilities in the model or inaccuracies in the solutions it gives you. So it's important to choose robust numerical methods and, really importantly, double-check your results.
So even with all the power of state space modeling, we got to be aware of potential computational hiccups and make sure that our models are both accurate and numerically stable.
Absolutely. It's all about using the right tools and techniques and always being critical of the results you get.
This all sounds pretty theoretical. Can we talk about how these models are actually used, like real-world examples where they're making a difference?
Oh, there are tons of applications. State space models, they're used all over the place in robotics, aerospace, electrical engineering, even fields like economics and finance.
Let's dive into some of those. You mentioned robotics. How are they used there?
In robotics, state space models are essential for controlling how robots move. Think robot arms, mobile robots, even those flying drones. They let engineers create algorithms that precisely control the position, the velocity, even the acceleration of every single joint or motor. And they have to account for things like inertia, limitations on how far a joint can move, and forces from the outside world.
So like for a robotic arm on a factory floor, the state space model would help figure out exactly how to move the arm to, say, assemble a product, making sure all the movements are smooth and precise.
That's it. That's what allows those robots to do those incredibly intricate tasks you see them doing in factories and all sorts of other settings.
Okay, what about aerospace? How do they help design and control aircraft?
State space modeling. It's a cornerstone of autopilot systems, flight simulators, even controlling spacecraft. It lets engineers design control systems that keep the aircraft stable, make sure it follows the right path, and deals with things like wind gusts or turbulence.
So when a pilot flips on the autopilot in a commercial airplane, it's a state space model working behind the scenes to keep the plane at the right altitude and heading in the right direction, taking all those external factors into account.
Exactly. That model is constantly crunching data coming in from all those sensors, the GPS, the gyroscopes, the airspeed indicators. It uses that data to figure out the plane's state and make adjustments to keep it flying smooth and safe.
Wow, it's crazy to think that this mathematical framework is running these complex systems that we rely on for our safety. What about applications that are closer to home, like in the electronics we use every day?
They're all over electrical circuits too, especially circuits with things like capacitors and inductor, those energy storing elements we talked about, your smartphone, your laptop, even the power grid. Those all depend on state space models for their design and optimization.
So these models are quietly working in the background, making sure our gadgets work right and our lights stay on.
Absolutely. They help engineers build stable and efficient circuits, analyze how those circuits behave under different conditions, even predict when they might fail.
Mind blown. It seems like state space models are everywhere. Okay, what about a super cutting edge area like self-driving cars? How are they used there?
Self-driving cars, those are a perfect example of state space modeling in action. They rely on them heavily to, understand their surroundings, plan their route, and move safely in those busy and unpredictable environments.
So the model takes in all that data from the car's sensors, cameras, radar, LiDAR, and uses that to figure out where it is, how fast it's going, and where all the other cars and obstacles are.
Yep, it builds this constantly updating picture of the world around it and uses that information to make decisions about steering, braking, accelerating, all in real time, all to make sure you get where you're going safely and efficiently.
It's amazing how this concept we've been talking about, defining a system's state, something that might seem kind of abstract at first, how that leads to all these amazing technologies we see today.
And that's the beauty of state space modeling, right? It connects the theoretical world of math to the practical world of engineering and technology. It gives us the power to analyze, understand, and ultimately control these systems, from the simple ones to the super complex ones.
Well, you've definitely given me a whole new appreciation for the power of state space models. It's clear this isn't just some theoretical stuff. It's a fundamental tool for tackling some of the biggest challenges out there.
Absolutely. And the applications, they're only going to keep growing as we create more and more advanced technology. It's a really exciting time to be in this field.
Sounds like it. You've given us so much to think about today. I'm already picturing all the systems I see every day and wondering how those state space models are working behind the scenes. Maybe that's something our listeners can do too. Take a look around you. I bet you'll find these models are playing a bigger role in your life than you realize. It really is amazing to think about all these models running in the background in so many different parts of our lives. Are there any other cool examples of how state space models are put to use?
Oh yeah, tons. Think about economics, for instance. Economists, they use these models to study things like economic growth, inflation, even unemployment. They can actually build models to simulate different economic policies and then try to predict what effect those policies will have on the economy as a whole.
So it's kind of like having a virtual lab, right? Where they can test out different strategies before actually, implementing them in the real world.
Exactly. And that type of modeling, it can really help policymakers make smarter decisions, decisions that affect all of us.
That's a really great example of how these models have an impact way beyond engineering.
And even within engineering, there are always new applications popping up. One area that's super exciting is bioengineering, using state space models in medical devices.
Oh, wow. What kind of applications are we talking about there?
Imagine prosthetic limbs that respond to the user's thoughts, or drug delivery systems that can automatically adjust the dosage based on what's happening in the patient's body. State space models can help engineers design these really sophisticated devices to be more responsive, more adaptive, and more personalized to the individual.
So we're moving towards a future where medical devices can work in sync with our bodies, constantly learning, constantly adapting to what we need.
That's the dream. And state space models, they're providing the mathematical foundation to make it all possible.
It's just fascinating how this concept of defining a system's state, something that seems kind of abstract at first, how it can lead to so many diverse and impactful applications.
It really shows you the power of math, right? Math can help us make sense of the world around us. State space modeling, it gives us a way to think about systems in a dynamic way, how they change over time and how we can actually influence that change.
It's like this powerful reminder that even the most complex things out there, whether it's a robotic arm or an airplane or even the human body, they can be understood and modeled, at least to some extent, using math.
And that understanding, that's what lets us design, control, and optimize those systems, and hopefully use them to make things better.
Well, you've definitely given us a ton to think about today. I feel like I have a whole new understanding of how powerful and versatile state space modeling really is.
It's been great diving into this with you.
And to everyone listening, thanks for joining us on this deep dive into the world of state space modeling. It's a field that's always pushing the limits, and I, for one, can't wait to see what new and amazing applications come out of it in the future. Thanks again.